Can two swimmers choose completely different paths across a river and still reach the destination at exactly the same time? It sounds impossible. But physics has a fascinating answer. Today's problem is a beautiful application of relative velocity, river crossing, and logical thinking. Imagine a river flowing steadily from left to right. On one bank is point A, and exactly opposite it, on the other bank, is point B. Two swimmers start together from point A. Both are equally skilled. Each can swim at 2.5 kilometers per hour with respect to the water. The river itself flows at 2 kilometers per hour. Now, the first swimmer is clever about direction. He aims slightly upstream so that the river current is exactly cancelled out. As a result, his path through the water becomes a straight line directly from A to B. The second swimmer takes a different approach entirely. He swims straight across, perpendicular to the river bank. But the current carries him downstream to a point C. He then walks back along the bank from C to B. Now comes the real challenge. How fast should the second swimmer walk so that both swimmers reach point B at exactly the same time? Pause the video right now. Draw the diagram on paper. Try to set up the equations yourself before watching the solution. Welcome to Numericals Studio. Our mission is simple. Let us make physics easy. Here we solve carefully selected problems for engineering and medical preparing students selected from standard physics books. Every solution is explained step by step, so you understand the concept, not just the formula. If you enjoy this style of learning, please like this video. Subscribe to Numericals Studio and press the bell icon so you never miss a problem. Now, let us solve this beautiful river crossing problem step by step. Now that we have understood the problem, it is time to analyze it carefully. We will look at the motion of both swimmers, one by one. This problem becomes much easier once we choose the correct frame of reference. There are two frames of reference involved here. The first is the ground frame. The second is the river frame. The velocity of the swimmer with respect to the ground equals the velocity of the swimmer with respect to the river plus the velocity of the river with respect to the ground. Let us set up a coordinate system. Take the river current along the positive x direction. And take the direction across the river as the positive y direction. Now let us analyze the first swimmer. He aims upstream at an angle theta, so that the river current is exactly cancelled. Resolving his velocity, the component along y is v sin theta, and the component along x is v cos theta. Since there is no horizontal drift for the first swimmer, we need v cos theta to exactly cancel the river current u. This gives us cos theta equals minus u divided by v. The crossing time for the first swimmer is the width d, divided by the y component of his velocity, which is v sin theta. Using the identity equation sin squared theta plus cos squared theta equals 1, we can find sin theta. Therefore, the crossing time for the first swimmer is d divided by the square root of v squared minus u squared. Now let us look at the second swimmer. He swims straight across, perpendicular to the bank. His crossing time is simply d divided by v. During this time, the river current carries him downstream by a distance equal to u multiplied by d divided by v. Let us call this downstream distance the drift. After reaching point C, The second swimmer walks back along the bank toward point B at a speed we call V0. The time taken for this walk is the drift divided by V0. So the total time for the second swimmer is the crossing time plus the walking time. That is d divided by v plus the drift divided by v0. Since both swimmers reach point B at exactly the same time, we set their total times equal to each other. Setting the total times equal and solving for v0, we get the walking speed of the second swimmer. Substituting the values, v equals to 0.5 km per hour and u equals to km per hour. The answer is 3 km per hour. This problem beautifully demonstrates the power of relative velocity. And it shows why choosing the correct frame of reference makes everything simpler. If you enjoyed this explanation, please like this video. Subscribe to Numericals Studio and press the bell icon so you never miss a problem. Together, let us make physics easy.